Okay, so 16 carbons in palmitate, we'll go over beta oxidation for it. So if we draw out palmitate, what do we have here? A carboxylic acid, and then this is 2 carbons, 3, 4, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Let's see if that is correct. With not the straightest line. Okay, but you guys get the idea if we're drawing a fatty acid chain with 16 carbons, right? So if we wanted to count the number of carbons, right, we can go 1, 2, 3, 5, 6, 7, 8, 9, 11, 13, 16 carbons. Okay. So the 16 carbon chain. Now, if we want to do beta oxidation, okay, we have a few steps of beta oxidation. What's the first step? What's the first reaction? It is a reduction. Okay. Was that right? No, I said it wrong. Because it's actually an oxidation, right? So we oxidize these to get energy. So it's an oxidation reaction. So we have an oxidation. Anybody remember what the second reaction is? Hydration. Okay. Then we have another oxidation. You should know this is a very important thing. And then finally, we have dialysis. Okay. So every time we do a step, we do a round of beta oxidation, we do these 4 reactions. Each time we do it, we get out an FADH2 from this step and an NADH from this step. And if we want to convert those, right, this is 1.5 ATPs, and this equals 2.5 ATPs. Right? We also get something else out of it. Right? We also get out of this step an acetyl-CoA, which we can stick into the citric acid cycle, right? And we can get out 10 ATPs. 1 turn of the citric acid cycle is worth 10 ATPs. If you want to break that down, it's because we get 3 NADHs plus 1 FADH2 plus 1 ATP. You can add that up. 2.5 times 3 is 7.5 plus 1 FADH2 is 1.5. 1.5 to 7.5 is 9. Add the extra ATP. So acetyl-CoA worth 10 ATP, NADH worth 2.5 ATP, FADH2 is 1.5. So every time we do beta oxidation, it's equal to 14 ATP. Right? So where we get this acetyl-CoA from is because of the 2 carbons. Right? That's what we're really talking about. Okay, so we break off those 2 carbons. And the 2 carbons we break off are actually these 2 carbons right here. And then we break off these 2 carbons. And so this dialysis step is coming in and breaking those 2 carbons off, right? Because coenzyme A has that thiol group, and that's what attaches those 2 carbons to coenzyme A, right? And so when we have this, what we have is a coenzyme A. Remember, we have to attach coenzyme A, bring it into the mitochondria, or bring it to the mitochondria, attach to carnitine, move it into the mitochondria, reattach to coenzyme A. So we're not really just breaking apart palmitate, we're breaking apart palmitate with coenzyme A, right? And so a new coenzyme A comes in and breaks those two carbons off. And now you have this acetyl-CoA, and the new coenzyme A is attached to the remaining 14 carbons. And then it does it again, and it's attached to the remaining, right? So we get an acetyl-CoA, and then we get a coenzyme A attached to the other carbon chain. That's why we break it apart from that end, okay? So if we're breaking apart two carbons at a time, you make a cut here for the first cut, right? That's our first cut. That's two carbons, carbon 1 and carbon 2. Now, the second time we do beta oxidation, we break off carbon 3 and 4, 5 and 6, 7 and 8, 12, 13, 14. Remember, once we break off 13 and 14, what floats away is that acetyl-CoA, and since a new coenzyme A came in and broke that last thing apart, you have two acetyl-CoA. The coenzyme A is what is doing that thiolate. Okay? All right, so this represents how many rounds of beta oxidation we can come up. 1 round, 2 rounds, 3 rounds, 5 rounds, 6 rounds, 7 rounds of beta oxidation. That's why even though we have n/2 equal to 8 here, we're in this number of carbons for a 16 carbon chain, right? We can get 8 acetyl-CoAs out. We only have to do 7 rounds of beta oxidation. And so if we want to do our ATP calculation, okay, we have 14 ATP, right, times 7 rounds of beta oxidation, radiated beta oxidation. Okay? But remember, the 7th round of beta oxidation nets 2 acetyl-CoAs instead of the normal 1, because you're breaking apart 4 carbons. 2 of those carbons attached to coenzyme A, 2 of those carbons attached to coenzyme A. So you get 2 acetyl-CoAs, right? You don't have to do an 8th beta oxidation step. So you also need to add plus 1 acetyl. Plus 1 acetyl. All right. So if we want to do that, we can do the net calculation. 7 times 14 is equal to 98. So we have 98 ATP plus acetyl-CoA, we already know is worth 10 ATP, 10 ATP. And so palmitate, through the process of beta oxidation breakdown, generates 108 ATP. However, you always need to remember this step. Before anything happened, we had to use 2 ATPs to activate that fatty acid by attaching it. Okay? So we always start with a -2 ATPs when we first attach that fatty acid to coenzyme A. And so the actual net of palmitate is 106 ATP. Okay. Now, if you had an 18 carbon chain or a 14 carbon chain or a 22 carbon chain, you just do the same thing, right? The only difference is going to be you draw this out further. You do more rounds of beta oxidation, right? you change the number for rounds of beta oxidation. Nothing else changes if you continually have a saturated, even carbon chain. Right? So that being the case, erase what I just did there. Let's look at an odd carbon chain. Okay? Let's look at a 17 carbon chain. Okay, so same sort of thing. We're drawing our 17 carbon chain. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 17. Okay, now I have my 17 carbon chain. I'm going to double check that I've written it correctly by labeling the carbons. 1, 2, 5, 6, 7, 8. Okay, there's not a lot of differences here. There's a set of steps for an odd carbon chain that you need to determine at the end. Everything else is identical. First off, let's remember off the top that we need to start with a -2 ATP, no matter what we're doing. We have to activate our fatty acid, attaching to coenzyme A, the expense of 2 ATPs. Great. Okay. So then what really changes? Well, we're still going to break off 2 carbons at a time. 2 carbons, 2 carbons, 2 carbons, 2 carbons, 2 carbons, 2 carbons, 2 carbons. And then you may think, oh, 2 carbons. This is the major difference. The last step, you can't end up with a single carbon attached to coenzyme A. You can have 2, or you can have, okay? So in the process of beta oxidation, you can't end with a single carbon. So we actually end with 3 carbons. And if we write all that out, right, it's the same deal where we can do 14 ATP times 7, right? Let's count them up. 1, 2, 3, 4, 5, 6, 7 rounds. Beta oxidation. Again, I'm going to abbreviate it beta-ox. Okay. Then plus, okay, here's the difference. We don't get an extra acetyl-CoA. Acetyl-CoA is 2 carbons attached to coenzyme A. We get something that is 3 carbons, and it is propionyl. So what's the deal with propionyl? Okay. How many ATPs is it worth? And net, it is only worth 4 ATPs. But let's determine why. Because the steps of why it's 4 ATPs is important. Acetyl-CoA is worth 10, propionyl-CoA is worth 4. Why is that? So the process for propionyl-CoA, right, is to take this and convert it into a familiar thing you'll recognize, succinyl-CoA, at the expense of 1 ATP. So we use an ATP to make succinyl-CoA, to convert propionyl-CoA into succinyl-CoA. Now we're starting in the citric acid cycle at succinyl-CoA rather than acetyl-CoA. If we follow acetyl-CoA to succinyl-CoA, what do we miss out on? What does acetyl-CoA generate that succinyl-CoA does not? Right? Okay, so acetyl-CoA becomes citrate when it's attached to oxaloacetate. Then protonatase makes it into isocitrate. Isocitrate dehydrogenase turns it into alpha-ketoglutarate. We generate an NADH at that step. So already succinyl-CoA is missing an NADH that acetyl-CoA makes. Then alpha-ketoglutarate dehydrogenase converts it into succinyl-CoA. So we're missing another NADH that acetyl-CoA generates, right? So 5 ATPs worth of electron transport chain donators is missing between acetyl-CoA and succinyl-CoA. Hence, acetyl-CoA is worth 10 ATPs, and succinyl-CoA is worth 5 ATPs. But because you have this right here, your net for propionyl-CoA is 4 ATPs. Okay, you do need to understand propionyl-CoA converted to succinyl-CoA, expensive 1 ATP, succinyl-CoA worth 5 ATPs. But if I'm just doing calculations, you can just count propionyl-CoA as 4 ATPs. And so the difference between a 16 carbon chain, 16 carbon palmitate is equal to 106 ATPs. Right? Then a 17 carbon chain is worth 6 less. Just based on Kerr's pattern and simple arithmetic, what would an 18 carbon chain be worth? What does an 18 carbon chain have that a 16 carbon chain doesn't? One more round of beta oxidation. What was it? No. What is one round of beta oxidation? Was it? No. How many ATPs is one round of beta oxidation worth? 14. That's it. All you get is an extra round of beta oxidation. So you get 14 extra ATPs from 18 carbons than you did from 16 carbons. So the answer is 120. Let's go to 19 carbon. So we're talking about net ATP calculations. So 14, it is 14. So for 18C, 14 times 8 plus another 10 minus 2. So 14 times 8 times plus 10 minus 2 is going to be I didn't do that math in my head. I just know it's 120 because I know that we only get 14 more. So what would 19 carbon? Yeah, you're absolutely right. 14 more than 17. Let's say you didn't know that. What's another way you can calculate it? If 16 carbons is 106 and 17 carbons is 100, what do you lose? You go up 1 carbon. 6 ATP because you lose it from the conversion of propionyl to succinyl, and then have a succinyl making 5 ATPs minus 1, 4 ATPs, right? So propionyl-CoA is worth 4, acetyl-CoA is worth 10. You have an odd chain that's 1 carbon higher than an even chain, you lose 6 ATPs. So 114. And so that's the pattern. And then finally, just so we can work backwards, then what's 15? Okay. So now you have a pattern to calculate any number of carbons through beta oxidation breakdown, converting to ATP. And you should also understand steps. Now, you should be able to do the steps because I might not just ask you questions about final ATP products. Okay? You should understand. Is that useful to go over for understanding beta oxidation? I'm going to stop recording.